June 25, 2024, a capsule punches through Earth's atmosphere at nearly 11 kilometers per second, trailing fire across the sky above Inner Mongolia. Recovery helicopters are already airborne. Ground crews in protective gear are already moving, and inside that small metal container, sealed and precisely weighed, are 1,935 grams of rock and soil that had never, in the entire 4.5 billion year history of this planet, touched Earth before. Because they came from the far side of the moon, not the near side, not the bright flat plains the Apollo astronauts walked across half a century ago. The side that permanently faces away from Earth, the side that looks out into deep space and has never once reflected a human footprint back toward a camera. China just brought home a piece of it. And when scientists finally opened that capsule and ran their tests, what they found inside quietly demolished several decades of assumptions about what the moon actually is. But here is what almost nobody said out loud in all the coverage of that moment. The samples were never the point, because what China is actually building right now, mission by mission, year by year, is not a scientific program. It is infrastructure, permanent infrastructure. And where that infrastructure is pointing changes the strategic calculation for every spacefaring nation on Earth. We will get to that. To understand why any of this matters, you have to understand that China's lunar program does not look like any other country's space program. Most programs are organized around individual missions. Design it, fund it, execute it, hold the press conference, figure out what comes next. That model produces remarkable individual achievements. It also produces gaps, pivots, restarts, and the kind of institutional memory loss that comes from treating each project as its own thing. China did something different. In the early 2000s, Chinese space planners laid out a roadmap that stretched across multiple decades toward a single coherent end goal. Not a landing, not a flag, not a headline mission, permanent operations. A system that could sustain itself beyond Earth. And they executed it with discipline that is genuinely rare in large-scale engineering programs. Chang'e 1 in 2007 never landed anywhere. It just orbited and mapped. Spent over a year photographing and measuring the entire lunar surface, building topographic data that every future mission would depend on. Not glamorous. Nobody writes major headlines about orbital mapping surveys. But every engineer who later had to land something precisely on the moon needed exactly that data. Chang'e 2 in 2010 went sharper. Better terrain models, higher resolution, more precise identification of safe landing zones. Again, foundational. Again, invisible to most observers. Then Chang'e 3 in 2013. China became the first country since the 1970s to soft land on the moon. The U2 rover rolled out across the surface. Interesting science, yes. But more importantly, China had demonstrated it could land hardware precisely on another world and operate it. The real turning point came in 2019. Chang'e 4 landed on the far side, something many experts had considered genuinely difficult, bordering on impossible, because the moon itself blocks all direct radio communication with anything on that hemisphere. China's solution was to place a relay satellite called Queqiao in a precise orbital position where it could simultaneously see both Earth and the far side, like placing a mirror in exactly the right spot in space so two rooms with no line of sight could suddenly talk to each other. It worked. Then came Chang'e 5 and Chang'e 6. Sample return missions. Not just landing, not just driving. Now China was drilling into the lunar surface, launching material back into orbit, docking autonomously above the moon, and bringing samples all the way home to Earth. First from the near side, then from the far side. First time in human history. Every single mission was a building block. Every single one taught engineers something they needed for the next step. You do not build a program like that unless you know exactly what you are constructing toward. Now the science. Because what was inside those far-side samples matters, and it matters in a specific way. Scientists and researchers have had access to Apollo samples for over 50 years. Those samples built an entire scientific model of lunar history. The moon formed roughly 4.5 billion years ago, went through a volcanic phase, cooled, and became geologically quiet somewhere around 1 to 1.5 billion years ago. That was the story. Textbooks were written around it. Careers were built on it. Then China opened the Chang'e 6 capsule. Analysis published in late 2024 dated some of the far-side basalt to around 2.83 billion years old, meaning volcanic activity on that hemisphere continued far longer than the models predicted. Other studies suggested the lunar magnetic field may have strengthened again during approximately the same period instead of simply fading, which is also not what anyone expected. And perhaps most surprising of all, the far side mantle appears dramatically drier than the near side, suggesting the two hemispheres are chemically far more asymmetric than anyone had assumed after 50 years of study. Think about what that actually means. The moon has been sitting overhead for the entirety of human civilization. It has shaped our tides, our calendars, our mythology, and we had the basic geology wrong in ways that only became visible when someone went to the other side and brought back a handful of rocks. The moon was not the simple dead world the textbooks described. It was stranger, more varied, more complicated, and suddenly these missions stopped looking like scientific exploration and started looking like something else entirely, prospecting. Because if different regions of the moon hold dramatically different compositions and different histories, the question stops being what is the moon made of? The question becomes what can we use? This is where the South Pole comes in. And this is where the project stops being about science. The moon barely tilts on its axis. Because of that, sunlight hits the polar regions at an almost completely horizontal angle, barely grazing the surface instead of shining down on it. Some crater walls near the South Pole are deep enough that sunlight never reaches the bottom at all. Not for a season, not for a century. In some craters, not for over 1 billion years. Temperatures inside them fall below negative 170 degrees Celsius, colder than the daytime surface of Pluto. And that extreme ancient cold has been functioning as a trap for almost the entire history of the solar system. Comets and water-bearing asteroids have struck the moon throughout its history. Most of that water was immediately destroyed by solar radiation or escaped into space. But the tiny fraction that drifted into those permanently shadowed craters hit something it could not escape. The cold held it, locked it in place, molecule by molecule. Over billions of years, scientific models suggest the polar regions may contain anywhere from hundreds of billions to potentially trillions of kilograms of water ice, concentrated in a relatively small number of craters near both poles. The uncertainty is enormous because nobody has actually gone down and measured it directly, not yet. But the evidence from orbital sensors is now strong enough that the scientific debate has largely moved from whether the ice exists to where exactly it is and how accessible it will be. And the reason that question matters so much comes down to one uncomfortable fact about space travel. You are sitting on the surface of the moon, in a crater that has not changed since before the first fish developed jaws on Earth, and beneath the dust around you is the feedstock for oxygen to breathe, hydrogen for fuel cells, and one of the most powerful rocket propellants humanity has ever used: liquid hydrogen and liquid oxygen. The moon's gravity is 1/6 of Earth's. If spacecraft could refuel at the lunar surface instead of carrying everything from Earth, the entire economics of deep space change completely. Mars missions become dramatically less expensive. Asteroid operations become viable at scales they currently are not. The moon becomes a logistics node, a supply depot at the edge of Earth's gravity well, a launch platform for everything beyond. That is what is frozen in those craters. And this is exactly where China is pointing its next 2 missions. Chang'e 7, targeted for around 2026, is not a single spacecraft. It is a coordinated system of 5 components working together: an orbiter, a lander, a rover, a relay satellite, and something no country has ever operated on another world before: a hopping probe. Ordinary rovers have wheels. Wheels work on accessible terrain. But the floors of permanently shadowed craters near the South Pole are jagged, ancient surfaces that have sat undisturbed for billions of years. Steep slopes, intense cold that would freeze conventional electronics within minutes, terrain that no surface map has ever captured in detail because no instrument has ever been close enough to map it. A wheeled rover cannot safely descend into that environment. So China designed a robot that does not need to. The hopping probe is built to leap approximately 10 kilometers at a time, flying through the lunar vacuum and landing inside craters where no sunlit pad exists. No stable ground has been assessed, and no instrument has ever operated. It carries a single critical instrument called LUWA, the Lunar Soil Water Molecule Analyzer. Its job is to find and characterize water ice in that terrain. Think about what that physically means for a moment. You are guiding a robot into a crater that has been frozen and lightless since before the Cambrian explosion on Earth. The probe cannot be controlled in real time. Signal delay makes that impossible. Everything it does, every assessment, every hop, every landing decision happens autonomously based on logic programmed before it ever left the ground. There is no rescue. There is no second attempt if the first hop goes wrong. One probe, one set of craters, one shot at the answer that 20 years of preparation have been building toward. And if it works, if LUWA detects accessible water ice in the concentrations the models predict, the entire downstream plan suddenly has a foundation. Everything that comes after depends on what this probe finds. Finding the water is only the first problem. The harder problem is what comes after it. Because building infrastructure on the Moon using materials shipped from Earth is economically catastrophic at any serious scale. Every habitat wall, every radiation shield, every landing pad has to survive launch across 400,000 kilometers of space, survive landing, and then function in hard vacuum under brutal temperature swings and constant micrometeorite bombardment. At current launch costs, that model does not work for anything beyond small robotic missions. So Chang'e 8, planned for around 2028, attempts something far more radical. Instead of bringing construction materials to the Moon, manufacture them there. The central experiment is a solar concentrator furnace that focuses sunlight to generate temperatures of roughly 1400 to 1500 degrees Celsius, hot enough to melt lunar regolith and cool it into solid structural material. China wants to print construction components directly from moon dust, landing pads that reduce the dangerous dust clouds kicked up during rocket touchdowns, radiation walls that shield equipment and eventually crew, roads that stabilize rover movement across loose terrain, structures that grow layer by layer from the surface itself without a single kilogram shipped from Earth. In late 2024, experimental lunar brick samples were mounted outside the Tiangong space station for long-duration real environment testing, exposed to actual radiation, vacuum, and thermal cycling conditions. Because laboratory results are not enough, the material has to survive the real thing before anyone commits to building with it 250,000 miles from the nearest hardware store. This is the shift that matters most in the entire program. The Moon is no longer being treated as a place machines briefly visit. It is being treated as a place machines can begin building permanent systems before humans ever arrive. Every piece of this program connects to every other piece. The mapping missions told engineers where to land. The sample returns revealed what the soil is made of. The ISRU experiments are teaching them how to build with it. The hopping probe will confirm where the water is, and behind all of it, a blueprint is becoming visible that was never really hidden. China calls it the International Lunar Research Station. For years, it sounded like an aspirational diagram on a conference slide. It does not sound that way anymore. The plan describes a permanent network near the lunar South Pole, power systems designed to run through the 2-week lunar night, communication infrastructure linking surface operations back to Earth, autonomous construction spreading outward as capability matures, not astronauts briefly visiting and leaving, machines building systems that stay, a presence that compounds on itself because it is sustained by local resources instead of perpetual resupply from Earth. More than a dozen nations have signed onto the framework. The direction is not ambiguous. And the United States, through the Artemis program, is aiming at the same region of the same moon for the same fundamental reasons. 2 major infrastructure programs, the same craters, different legal frameworks, no binding agreement about what happens when hardware from different nations ends up operating in close proximity to the same water ice deposits. The Outer Space Treaty prohibits territorial claims, but says nothing specific about resource extraction, nothing about operational safety zones, nothing about competing operations sharing a geography. The Artemis Accords include provisions about safety zones. China and Russia have declined to sign. This is not a distant hypothetical. It is the current trajectory of two programs both making real hardware decisions based on their own frameworks. And the permanently shadowed craters both programs are targeting may contain far more than water, organic molecules from ancient comets, isotopic records of early solar system chemistry, material preserved in conditions of such extraordinary stability that it may hold information about the early Earth that no longer exists anywhere on this planet. Once large-scale extraction operations begin in those craters, that record ends permanently. There is currently no international framework governing what gets protected and what gets used. History is consistent about what happens in that situation. The irreplaceable things disappear before the frameworks arrive. The Moon has been waiting 4 billion years. It deserves more careful treatment than that. These are real concerns worth raising seriously, not as a reason to stop, but as a reason to insist the frameworks come before the extraction rather than after. But here is what remains true regardless of legal uncertainty or timeline slippage. The capability accumulation is real. The far side landing happened. The sample returns happened. The relay satellite worked. The science was genuinely surprising. The engineering problems China is now working on are hard, but they are engineering problems, not physics problems. The direction has been clear for 20 years and it has not changed. The Moon is being treated, for the first time in human history, not as a place to visit, but as a place to build. And the country that builds functional infrastructure at the South Pole first does not just win a space race. It establishes the operational template, the legal precedents, and the physical presence that shapes everything humanity attempts beyond Earth for the rest of this century. Infrastructure is leverage. It always has been. The country that builds the roads decides where the roads go, and the roads are being built right now. Leave a thought in the comments on this one. Here is the question I keep turning over. If water ice extraction at the lunar South Pole becomes real, and one nation builds the refueling infrastructure before anyone else, is that more like owning a port that others can eventually use, or more like owning the only freshwater source in a desert? I genuinely want to know how you think about it. If this was worth your time, you know what to do. Next one is already in the works.